Okay, so it's a pleasure to be here. This is my third time in Montreal in HSA. I'd like to thank George and Michelle for the invitation. And my talk today is a disclaimer, has some overlap with my first talk like 4 years ago, but there is some new stuff, okay? The research essentially is about store layout. And what we have here is store-wide retail shelf space planning. So a mouthful, but this is to say that what we're doing is we're doing horizontal store space allocation. In the literature, most of the work is on so-called planogram type of approaches, where people assign things vertically, typically different stock keeping units, SKU, in the same categories. What we're doing here is different. We're looking at all the categories in a store, let's say in a supermarket, the different categories, so milk, sugar, coffee, so on, and we are deciding where to assign these horizontally. And this is a somewhat new research stream. We started this ourselves like almost 10 years ago, and concurrently, other people started doing this. One of the motivations for why doing this right now is that there is lots of data available now on people movement inside the store. Unfortunately, we don't have this data ourselves, but we have proxies for this data. Another reason is that people are trying to learn from manufacturing facility layout and applying a retail facility layout. So this was kind of a transition from the lessons learned from manufacturing, trying to apply them in retailing, basically. Because in manufacturing, you lay out different departments in a plant or in a warehouse. Here, we're laying out different retail categories which act as many departments on the floor plan of the store. So that's the overall topic. And basically, I don't have the full title here, unfortunately, but the new element today is we're having multiple objectives. We started doing this 10 years ago with the objective of maximizing the retail profit and mainly impulse profit, the things that the money that the retailer makes from you buying things in an unplanned manner. Recently, we added other objectives. We have two more objectives, one on convenience shopping, in order not to have someone move in the store forever to find what they want. And second, something that has to do with health. So if you have a pandemic or some health situation, we don't want people to spend lots of time in the store. The challenge is to balance these objectives of consumer welfare or consumer well-being with the basically profitability of the retailer. Okay, so that's kind of an overview of the research. Today I'll give some motivations. I already gave some of those. I'll talk about the problem and the scope of the decision. I'll briefly review the literature, present our models and assumptions, and then I'm going to illustrate the application within 3 case studies of 3 different stores, one in Massachusetts, one in Beirut, and one in Normandy. So interesting cultural retailing journey it was. And then I will present some conclusions and idea for future work. So one of the main motivations for us is what's happening in the retailing industry and theory, actually. So in the last 10, 15 years, there have been more and more work on retailing having quantitative nature. Okay, so and some people are saying that this is like what happened on Wall Street. On Wall Street, finance was like stock picking, then it became quantitative finance, and people with math and physics background are now doing very sophisticated models. And retailing, something similar is happening, and I can testify to that firsthand. I myself worked for around a year with a retailer in the Northeast called Hannaford, and there we were using some statistical analysis. And many of my current colleagues are working now with Walmart, with Target, with Amazon, doing these kind of things. So I'm happy that people my age are finding jobs. So it gives me options in retailing, applying things like this, especially in Walmart, Amazon, and Target. We lost a very good faculty in our department last year to Target, actually. So the other motivation is basically impulse buying. So impulse buying is important, especially in industry like supermarkets. So impulse buying, it means you go to the supermarket, you want to buy healthy stuff. So milk, cheese, eggs, the fast movers that, by the way, retailers never make profit from. So these fast movers are, I used to work in a supermarket. The retailers lose money from these, but they make money from the other stuff. So impulse buying is actually the unplanned purchases is what make supermarkets survive, you know. So, and if you know about it, first of all, it ruins the fun. And if you avoid this impulse buying, you can actually save money. Okay. For example, what you see on I don't know if they still do them then now, the first page of the weekly flyer, if you have a supermarket like Carrefour, I don't know, you have your, typically the first page of the weekly flyer, these are loss leaders. So you go, if you only buy these, the retailer loses money. But the idea of the retailer, you see these loss leaders which are sold below cost on the first page. You go to the store and you get hooked on other things which are called hedonic or basically impulsive products. So that's the idea of the research. It might sound evil, but that's how retailers survive. And now we're trying to make it less evil by adding these objectives that take into account the retailers, the customers' welfare. Another motivation is the issue of shopping convenience. So some surveys done by consulting companies, including McKinsey, I think, show that customers value convenience a lot. So one survey showed that convenience ranks third in what customers care about in shopping in a store. We're talking here only shopping brick and mortar or physical stores. So this survey showed that most customers rank convenience third after quality and price. So they want to shop in a store, they want to have low prices, good quality, and they also want to be able to find their products quickly, basically, in the store. So convenience is important. And more and more people are saying that they care about convenience more than before, basically. So these, again, are white papers from the industry. Another motivation is the issue of health. So we all remember the COVID days. Hopefully it will not happen again. But you all remember those days when we had to keep social distancing and we were advised to opt for curbside pickup. And even if we're going out, take a list with you and stick to the list. If you stick to the list, the retailer is damned, basically, you know. So that's the part of the challenge that retailers faced in the epidemic. And if you're in line, we have to be respectful and so on. So this is one case study of a retailer called Wegmans. Wegmans was a retailer selling fresh products, and they were famous for like free samples and tasting and friendly environment. So you go there, you have free samples, you chat with the vendors. When the epidemic came, all of this became impossible. So they can no longer do this. They closed for a while, but then they reopened, and they reopened like this. Everything was packed and covered with plastic. They were cleaning the surfaces the whole time, and they were giving the impression of cleanliness. So their new business model was now no longer the fresh product free sample place. We are now the healthy place. Come here and you will never get infected, basically. So this example shows that retailers changed their assortments and the placement of their products in an epidemic. So one objective of our research is, if this happened again, hopefully it won't happen, how can the retailers be prepared? How can they redesign their store layouts to protect the customer health at the same time remaining profitable, remaining in business? Okay. So these are kind of the motivations in terms of the problem scope. Again, so you go to the store, you want to buy this healthy stuff, and you end up being these unhealthy stuff, which people in economics call hedonic or pleasure-inducing products. They're bad for you, but we all buy them. I admit I buy them. These are like makeup, cosmetics. So yeah. I myself go to the store to buy ice cream only. So I go to my wife does the actual shopping. I go and buy ice cream. So I do go directly to the impulsive products. So anyways, so no issues. All right. So and I like Ben and Jerry ice cream because I like their social standard. All right. So in our research, we decide about basically two main decisions: the location of a category in the store and how much shelf space to assign to the category. Okay. So we take a bird's eye view of the store, and we say, okay, what do you want to place? You have maybe 100 categories. Where do you want to place those? And one shelf could accommodate multiple categories. So where do you want to place those, and which shelves, and how much space to assign on each shelf? These are our decisions. And again, we have three objectives: impulse buying, convenience, which we capture by walking, and customer health, which we capture via the time spent in the store, and we argue that the time spent in the store is a proxy for infection. So if you minimize time spent in the store, you minimize infection. We will use some health literature to justify that. In terms of the big picture, this is a study from Germany, some researchers at TUM. They looked at all the different decisions in retail space planning, and they basically classify what we do here. So what we're doing is we decide on the size of the categories and the sequence of where categories are placed, basically. Okay. So, and they say that these things happen every couple of years and every year. Even though our own experience and our belief that these things happen every few months. I mean, not at a drastic level, maybe, but we all go to our favorite supermarket and we see things moving from aisle 7 to aisle 11 to aisle 9. So it doesn't have to be a major remodel, but the retailers do change the placement of products in the store to respond to different marketing needs. I'm sorry for this. All right. So in terms of the literature, again, there is some background literature, including some by George and his collaborators, and other classic literature, mostly on the planogram problem, how to assign things vertically in a category. We're taking the store-wide planning, which we can also call horizontal placement. We believe we came up with the term store-wide planning. There is an issue of property for the name, but anyways, we think we did enough research to earn that we the label for this. So store-wide planning means we assign things horizontally, and we've been having a paper every couple of years on this with different, and we're a team of different co-authors, basically. And other people follow. Other people are doing some work. So there's lots of works here, but if you look for these works, they are very much spread out. So we put some effort. We wrote a book recently. I'll show you the book. We edited a book where most of these authors developed some works, and there's some background literature on pricing and assortment and inventory, which we also made some contribution to over the years. This is the placement of the research with respect to the literature. I don't like these tables very much, but many journals now require this. So this is for each journal, basically. they ask for this.
The strategy is not to include it, so the reviewers will ask for it, and you have the impression that you are satisfying the reviewer.
I'll do it like this from now. Okay. But anyway, they take time to develop these tables, but they do show something. I mean, so here our work basically is we're looking at category location in a store and category size, and we have multiple objectives, and we use ILP. So our approach is more analytical in nature. So these are the distinctive feature of our approach. Other works in the literature, they use heuristics, taboo search, and other heuristics. And very few of them, except for the work of Professor Smith from, I think she's at Auburn University, no one considers multiple objectives, even though multiple objectives are at the essence of retail space planning. This is our edited book. It paid for coffee for a couple of months. Now I get emails from the publisher. Sorry, the money is not enough to send it for you, so I'm not getting free coffee anymore. But for a couple of months, I was getting free coffee from the book. I was happy with that. But the nice thing about this book, many authors in this area were having hard time like publishing some work, including us. So this work has basically an assortment of very good rejected papers, basically, so that we polished and put here. Yeah. All right. So in terms of our model and assumptions, the key thing is the demand model, okay? And the demand model is based on the traffic density. And our initial demand model is something like this. So the customer comes to the store. Let's try to get a pointer here. Let's see. 1, 2. So the customers enter the store, and then basically they could go to shelf B. So B is the shelf, or not go to shelf B. If they go to shelf B, then they might see product P on shelf B, and we assume that the visibility is proportional to the space assigned to product P like parking, on shelf B like Bacel, basically. So this is SPP, is the shelf space assigned to the product. And this is called the visibility assumed to be linear in the space assigned. And once the customer sees the product, so I see the coffee on the shelf, I will not buy it for sure. The probability of buying it is something called IP, the impulse purchase rate for product B. And this metric is controversial, let's say. Some people in marketing say this exists, some say it doesn't exist. But we've been using it, and other people have been using it, and we feel it makes sense. We surveyed people on it. People seem to customers seem to find it intuitive. But also in our results, we did some sensitivity analysis. So even if it's not easy to estimate this, but our model is robust to changes in this particular parameter, which is the impulse purchase rate. Okay. So if the customer decide to buy, then they will have a profit, the profit margin from the product. And here, for now, as an initial cut model, we are focusing only on impulsive products. Later on, we're going to introduce other products. Yes, Michelle.
So if you want coffee, not there.
What's that?
If you want to buy coffee, it's on your list. It's
Yeah.
not there.
It's in the follow-up model. Yeah. So we'll show you how to the coffee in a bit. Yes. True. So this is the first model we developed like maybe 10 years ago. And this model, to simplify things, so here we have the the traffic density, which can be seen as the probability of a random customer entering the store going to shelf B. That's what we call traffic density. And this depends on two things: the location of the shelf in the store, so shelf close to the entrance and exit have a high density, and what you place at the shelf and close to it. So in our initial model, we ignored the effect of nearby products on the traffic density, because the capturing that creates some dependency in the model, some nonlinearity, which makes it hard. So we said, as a first cut model, let's ignore that. We end up with this huge multi-knapsack problem, kind of. So ILP, but very large in size. So here the objective is to maximize the impulse profit per customer, average impulse per customer. We have some constraints like these, which ensure that the shelves is contiguous, which means you place coffee next to the coffee and milk next to, you don't have like coffee, then milk, then coffee, basically. That's what's happening here. So anyway, this was a promising problem to try to solve, and we tried hard with existing solvers. It didn't work. So we use a technology of, or a technique, I'm sorry, of divide and conquer. And our approach was that, look, these shelves, they can fit particular products. If a shelf is, for example, refrigerated, it will only fit certain products. If it's a freezer, it will fit certain products. So there are some practical constraints which make, in a sense, the feasible region less. We have these constraints here, but instead of having the model look for them, we decided to use those in a pre-processing. So long story short, what we did is we solved a priori in a pre-processing step. We solved all the possible assignment to a given shelf. So we take the shelf in the back there. We say, what are the categories that can fit into the shelf? We consider them all, and we solve a single knapsack problem to find the optimal size of the category to assign at a given shelf. So the problem here is assigning group G to shelf B, given that group G is feasible. It is of the same type, whether refrigerated or not, and it fits on the shelf. Okay, so we have some feasibility check. After we pass the feasibility check, we solve the single knapsack problem, and then we find the size of the categories on this shelf. But we did this for all the shelf group combinations. So we divided products into groups, and the number of groups were chosen to be equal to the number of shelves, and we did all the possible combinations, basically. Okay. And then once we have this, so one shelf problem, it is solvable in an easy way. We went to the next step where we now assigned the groups to the shelves, given that now we have an idea of the profitability. So this theta here, sorry, this psi here, this comes from the first model. So now in a pre-processing step, we know if you put this category here, how much profit you would make. If you put that category there, how much will it make? And what we did here, we looked at assigning groups into aisles. So in an aisle, maybe you have two shelves. So we found in this model here, we picked all the different groups that go into these two shelves, but we do it for the entire store. So the store-wide planning is happening in this second phase problem, where we are assigning groups to shelves in a sense, given that they have this kind of aisle structure. And this is what they call in the optimization literature a generalized assignment problem. And luckily, this can be solved very easily. So in our experience, we could solve this in seconds. Okay, so this made the computation much easier. And we applied this to a mid-sized store in New England. Management was not cooperative. We have very dedicated PhD students at the time. One of them might be with us today, our first the lead author on this work. So Tulai did a good job going to the store, drawing the shelves, drawing the content of the shelf. So lots of hard work to map the store plan, because the retailer would not approve it. So we did this so-called industry espionage, basically, with phones and going to the store and measuring things sometimes by feet or something, So we had to do what we have to do to get the data. And then we come up with something like this. So this is the store plan, the store floor plan, and we have the exact assignment of categories to the store, basically. Okay. And using this, we estimated that we can make an improvement of 32% in impulse profit, which is good in an industry where the profit margin is less than 1%. 32% improvement. You go from 1% to 1.32% is not bad at all.
This improvement is coming essentially
From moving things around. So the impulsive products were not placed in the ideal location. So they were placed in hot areas close to the entrance and exit, basically, and that's what made the profit higher here. That is the main reason for this. So this is the question. So assign impulse product to hot locations, and we give them more space. So another thing is we gave these impulsive things more space. We gave them more visibility, basically. And then we looked at, okay, I think this is the one referees ask good questions. So they were saying, okay, we're maximizing impulse profit. What's happening to the customer walking a lot on the store? Because now we're spreading this impulse buying, and also we spread actually also spread the magnets or the fast movers. So we spread things in the store. The referees were asking what's happening to the poor customer. So we estimated the walking here, the walking effort by this formula here. Okay. This is, again, now post-optimality analysis. And we found that the walking increased by 8%. So not too bad. I mean, you make 30. That's fourth objective. Maybe walking in nature is better than, even in the snow, better than walking in the supermarket, right? I got annoyed myself walking alone. I don't know about you. Yeah, so not bad, but we thought maybe we can do better, So the next research questions came naturally. So this is not bad. And what happened in big stores? So we have a huge store, you spread things around, it becomes really a pain to look for things, So luckily, thanks to a collaboration with a school in France, we worked on a big store in Normandy, and we talked to the management. They were supportive. We hope to get some good data now, but it didn't go through a lot. But at least we had some support from the management. But now here we are. We use the same two-phase approach as before, but we have a second objective of minimizing basically walking in the store, using a similar method to what you saw before, but now this method becomes indigenous. So in the first study, walking was exogenous, was estimated after running the model. Now we optimize over that. So phase one problem of group to shelf is the same, but now we have a phase two problem. And the phase two problem is about minimizing walking. We tried to do that. Walking from shelf to shelf turned out to be very hard to solve. So we divided the store into areas or departments, and we tried to minimize walking between different departments. So the store was big. We divided it into 6 departments, and we minimized walking across these different departments to make the model a bit tractable. And we end up with something like this. So this is now the phase two problem of this two objective model. And we have two objectives here. We want to maximize impulse profit, minimize the walking. And this we get from the phase one problem like before. The problem is here we have some nonlinearity. Now, modern solvers such as Gorobi can do this right now. One of the associate editors actually brought this to our attention. So the solver can do it, but it takes hours. That's the problem. So it's doable in solvers. but it takes time to solve. That's the challenge we've having. So we've been having with these, that they are not easy to solve. So we limit the solving time. Some instances solve within like an hour, some take more than an hour, some take 30 minutes. So this is a hard problem to solve.
Is it an issue?
Given that the planning is like around twice a year or a couple of months, we don't believe it's an issue. But it's good to be able to get solutions quickly. And I believe if you dig deep into this is a quadratic assignment problem. So we didn't have a chance yet to look at that 80s and 70s literature on quadratic assignment and apply these techniques from there. I think we could even we could have some ways to improve the running time. So this is the quadratic assignment problem. It solves what takes time, and so it's tricky. So the equality constraint actually make life difficult with the quadratic thing over here. So it's not really a full smiley face. It's a small. It's we manage for practical reasons this works, but I think some work can be done over here. And basically we linearize these, and now we apply them to this big store. So the first store was called Gridsy because it's grids layout. This one is called Babo. Anyone knows what is Babu or Babo? Any ideas? Okay. This is big and by objective, basically. That's the big store. So it's a big store in Normandy, probably one of the biggest department stores I've seen in my life, huge store. And it was really hard to get the data from it. And the company changed their mind. So luckily we have some money. We commissioned a marketing company called Qualtrics. Qualtrics called the customers on our behalf. They got the receipts from them, and using the receipts of what customer bought, we were able to estimate walking distances in the store. This is how we got the data for this one. And these things you see are the areas. So these red things are the areas that we define in the store. So we define the second objective in terms of walking from here to here, from here to there, and so on. Okay. So this is the second store, and the main result for the store is this efficient frontier. How do we get this? I mean, you cannot solve for two objectives at the same time. You do this trick of making one objective a constraint, and we use something called the epsilon constraint method. And we obtain these solutions over here. All of these are Pareto optimal solution on the all the solution on the blue curve are Pareto optimal solution, and in the sense that they are either they're not dominated on walking or impulse profit. And we see here what we were doing before we were here. We're maximizing impulse profit, and as you can see here, this gives a high profit but loss of walking. If you look at other Pareto optimal solutions, you can go to here. So here you achieve almost the same profit, but with much less walking. And as you can see here, the walking is huge. This is in feet, so this is like a customer walks 1 kilometer in this store. Basically, it's a huge store. Basically, it's healthy to walk 1 kilometer, but still. But the idea is if you optimize over, if you do multi-objective, you get solutions like these. And they are good. If you care about customers only, you minimize the walking, you'll be here, and that hurts your profit by half almost. So the argument is that, or the main insight or findings here is that multi-objective programming allows us to exploit solutions like these that otherwise we could not see. And these solutions strike a good balance between profitability, the profit is almost unchanged, and walking. Okay. Another interesting finding, which pertains to this store in particular, that the current layout is here. So in the current layout, our estimate of the impulse profit are at the low end, and walking is high. So it seems right now the retailer is trying to make it easy for the customers and not placing the products in ideal locations. So what we achieved dominates the current allocation by huge magnitude. Okay. So in terms of so our solution, which is too good to be true, basically, it boosts impulse profit by 82% and reduces walking by 11%. Okay. Now the walking reduction is by design because we have it as an objective. The impulse profit significant increase, we believe, is due to the store size. So the store is huge. You can do lots of mixing and matching, and compared to the store we had before, we have more opportunities of moving things around. So that's why we find this result to somewhat be reasonable. So we can spread things around and we can do more mixing and matching. So of course, the referees were skeptical, and we understand that. We did lots of sensitivity analysis. So these curves here, these efficient frontiers show you the effect of different profitability levels. For example, here we're looking at different values of the profit of the products. We looked at different impulse purchase rate. And this was good because, so the impulse rate is admittedly something hard to estimate, but as you change it, things do not change very much. So we're not too sensitive to the impulse purchase rate. We changed the store topography, the distance between departments. We got these. And we changed things like the profitability of the products also. We got things like this. So long story short, it seemed that the results, they hold in different scenarios. And in all cases, the current solutions which we have over here, we were doing better than those. So in all of we changed the parameters, we estimate the current allocation of the retailer and our own assignments, and it seems we are always doing better than the current allocation of the retailer. Okay, so that's the first model. Now the third model, which we worked on after concurrently, had a main objective of introducing into the mix the effect of product location. So all of this work now assumes that the traffic density, the probability of going to a certain shelf, depends only on the location of the shelf in the store. We added in this work here the effect of the contents of the shelf and the shelf surrounding it. Turns out there is a model in the 50s by Farley and Ring that uses some attraction ideas, and that model allows one to have a kind of a global traffic model. Any change of allocation in the store would affect density in the entire store. So this attraction model looks something like what you see over here. And eventually we had a regression model that combine both KB, which is the location-based traffic density we had before, and this phi B norm. This is the kind of normalized attraction on shelf B from other shelves. That's what we have here. We use beta regression, we end up with theta B like this. And the problem with this is it added more nonlinearity to the model. So that's one issue we had. We used some linearization techniques to make this manageable. And eventually this worked. So the model has what's called ripple effects. If you change the allocation of any two categories in the store, the traffic in the entire store changes. This is what's interesting about this model, this ripple effect. Like you throw a stone in a lake, you have these ripples here, you take the ketchup from aisle 9 to aisle 11, and the whole traffic changes. That's what this model does. Anyways, the resulting, again, we're doing this phase 1, phase 2 business. Phase 2, I was assigning groups to shelves. Now looks much more complicated with these nonlinearities. And this added more difficulty in the solution problem. And we, again, linearized these nonlinear constraints. We solved these. They took some time. But eventually, we managed to get some reasonable solutions. We applied these to a store in Beirut, which we call Ripley. And Ripley is a medium-sized store in Beirut, let's say, in one of Beirut's suburbs. And it has interesting categories such as the ones here, Arak and other things. So we applied this to the store in Beirut, and we had full cooperation of the supermarket owner. I mean, it was the cousin of, I don't know who, from one of my students. So full access to data, to the store, to everything. So we had a very good access. Anyway, so we had the customer receipts, we had the and other things. We did market basket analysis, we estimated fast movers, and so on. And we had data from 40,000 receipts. We took the 40,000 receipts and we treated each one of them as a traveling salesman problem. So we solved 40,000 traveling salesman problem. And this allows us to estimate density in the store because we have a regression model. We need to be able to estimate the dependent variable. We need to have the traffic to estimate the traffic. What modern companies do, they put sensors on carts, and from that data, they estimate the traffic density. Other companies track the customers, these things, mobile phones, and from these, they estimate the traffic. We didn't have access to the sensory data. But with the e-receipts and this traveling salesman approach, we were able to estimate the density of the different customers in the store, basically. So from that, we were able to calibrate the regression model, and then we solved the problem, and we went from the current allocation to the optimal allocation. And because the store is somewhat small, you don't see much change in the allocation except in the middle shelf. So if you look at the middle shelves here, for example, here and here, you see some more traffic. So the way the model worked is we put the fast movers in the back, kind of, and this made people go more through the middle shelves. It created more traffic here, basically. Okay, so this was the gist of this model. And we had an 85% improvement in impulse profit. So even though a small store, but because now we're capturing, we believe, traffic in a better way, we could report 85% improvement in impulse profit. And the main insight was that where is this profit coming from? It's coming from placing the products in the right place. We found that the size of the category does not matter very much. And this is interesting because in the classical literature, it's all about the size, how much size of the sign on the shelf for SKUs. Here we found that no, in this horizontal planning, the size of the category does not matter much. I mean, of course, we have a lower bound and upper bound, and you see the lower bound and upper bound here. But within these bounds, what matters is the location. So the location really is what matters the most. And we also find the model to be robust to input parameters. So things like impulse purchase rate and other things, we found that really, even if you make a small mistake in estimating those, it's not a big problem. Okay. So all of this is work done, unpublished, and we're happy with it. Our current project now, and we'll have like maybe 5 to 7 minutes. Our current project is to try to assign health considerations. I mean, they can be health and they can be other things. So maybe you can give me ideas here. But the main thing is to say that we want to limit the traffic in the store. Because having too much traffic, we're saying here, is not good for your health. You go to a store, it's too busy. You have a flu season, you have an epidemic, you can catch something. You know, that's the idea of this. So that's the idea. And we changed the demand model now because the traffic now comes from people who buy impulsively and who buy in a planned manner. Before, we were focusing on profitability, and the planned purchases didn't matter very much. Now, planned purchases create traffic. So we changed our model to have this a new dimension, where people go to the shelf in a planned manner or not. If they go in a planned manner, they will keep looking for the product to find it. So if I have, we're assuming here, if I have milk on my list, I will keep looking for the milk until I find it. That's the assumption here. Okay. So this is how we account for the plan and the coffee also. How I account for the planned products. Okay. So same demand model as before, but we have now the effect of the basically the fast moving goods, or the lost leaders, if you want to call them like this over here. So what we did is we estimated the time a customer takes to shop a given shelf based on the allocation. And in doing so, we use this metric called tau. This tau is the time it takes to find the product and pick it up from the shelf. Okay, so we find in the literature in marketing, many studies estimating time spent in the shelf and time it takes to shop items. So basically, using those marketing studies, we could estimate this tau, which is the time it takes to basically shop one product. And tau is based on tau, we could find what we call WB, the time spent at shelf B. And then the time spent in the entire store becomes this weighted average. So if the theta B is the probability of going to shelf B, then the time spent in the store becomes something like this, a weighted average of the time spent at different shelves, with the weights being the traffic itself. And again, this metric tau includes search time, walking time, and checkout time. And we estimated those based on basically the ratio of total time spent in the store over the average basket size. So it was hard to estimate these. We looked in the marketing literature, we found total time spent in the store, and average basket size. So this includes everything, basically. If you spend in the store one hour and you bought 15 items, it took you 4 minutes per item. This was our approach, kind of, to estimate this tau. And there is lots of studies, interestingly, from all over the world, from Europe, North America, Australia, estimating these two metrics: total time spent in the store and average basket size. So the quantities we're using are inspired by these different studies from all over the world, basically. Now, why does W matter, the time spent in the store? Because in health, there is this Wells-Riley model, which says that the probability of infection, P, so if you go to a store, the probability, if I go to the store, the probability of me getting infected by an epidemic is given by this, where the only thing which the retailer can control really here is W. So Q, P, Q, and I are things which have to do with airflow and the height of the ceiling and physical characteristic of the stores. So things which you cannot change once the store is built, So people in epidemiology, people in engineering, they use this, and health, they use this Wells-Riley equation to estimate the probability of infection based on how much time the customer spent in the store, W, and other characteristics of the building itself. So this is the idea. So what the retailer can control is W. Yes.
W is equal to 0.
W is equal to 0. It will be zero infection.
And it goes to infinity.
Yeah. Makes sense. Huh? But thank you for I like this. A quick check. Okay. Yeah. So this was used a lot in the COVID time. Some people were publishing very fast. So they were using this model to estimate the probability of infection during the COVID time, basically. So it has some, and these are respectful health publications, basically, epidemiology and health and so on. So the main insight is if you minimize time in the store, you minimize the probability of infection. So now we can claim that we're working on health, but really we're working on W, the time spent in the store. So which I don't mind, because I'm not really too much into infections and health and stuff. So not my cup of tea, but again, makes someone happy that we are looking into the customer well-being, which I want to do, but I don't want to go too much into health. But anyways, so now the part which I like about the research, which is the queuing aspect. So you can use queuing theory, something like Little's law, to estimate the average number of people in the store. So Little's law says that the average number of people at shelf B, LB, is the arrival rate to shelf B, which is lambda times theta B, times the time spent at the shelf. So from this, we estimate the average number of people at shelf B. Average number of people in the store becomes L, the sum of those. So if you want to minimize the total number of people in the store, which could be good in an epidemic, you can do this, basically. These are alternative objectives that we will experiment with eventually. One thing we experimented with, I'll show you shortly, are social distancing constraints. Remember the 6 feet? Some people say 3 feet. Some people said 6 feet. Some people said 12 feet, The bigger the distancing, the more you constrain the retailer, basically. So we tried to see the effect of this social distancing constraint on the retailer profit. And here we're saying that if you want to have 6 feet between two customers on average, then the number of people at the shelf should be less than the shelf length over 6. That was how we got this constraint. So this is a 6 feet distancing, and the shelf length is measured in feet over here. I'm running out of time almost. Now using nice results from the MG Infinity queuing system, the infinite server queuing system, which some people refer to, interestingly, as self-service queue. So people in a supermarket, no one services them, they service themselves. So we use this MG Infinity results, and from here we know that the number of people in an MG Infinity is a Poisson random variable with mean LB, okay? This allows us to analyze the risk, or to put to look at the variability of number of people in the store. Not just number of people, variability of number of people in the store. And we can then do things of this form, try to minimize the probability of having less than 6 feet between people. So this is the idea of this over here. And we can do things like we can do things like this and take some safety measures. So this is basically one standard deviation. So this way you're being a bit conservative. You're saying 6 feet plus some safety margin. which is captured over here, basically. And we can also minimize var type objectives. So we can, instead of minimizing the average number of people in the store, we can minimize the 95th percentile of that. So this could be interesting if you feel that there is high variability in the number of people in the store. Instead of minimizing the average number of people, we could minimize the VAR, the value at risk of the average number of people. Can I take 2 more minutes to finish?
Yeah.
Sure. Thank you. So the store we had is called Ripley. I asked one of the AI tools I used to create a logo for this Ripley store in an epidemic. It gave me this picture over here. Okay. And essentially, we got this. So now this is similar to before, but the objectives are different. We have on the horizontal axis the time spent in the store, not the walking. The two things are similar, but this is time spent in the store, not walking, basically. And on the vertical axis, we have the impulse profit. And again, we have this nice shape of the efficient frontier. So what we were doing before was here. We were maximizing impulse profit and making the customer spend too much time in the store. Not good in an epidemic. In an epidemic, you could do this maybe. Lose some profit, which is honorable. But at the same time, the customer spends less time. So these solutions such as these are good compromises. Okay. So again, we tried to do sensitivity analysis on this. So here we are changing mainly 2 things. The amount of social distancing that we want, 6 feet or 3 feet, okay, or no social distancing. And we're changing also the traffic intensity, how many people comes into the store, okay. It seems, given that our store is small and not too busy, that most things don't matter much except for this thing over here. So what happened here, we have a 6 feet social distancing and a high traffic intensity. So lambda equals 0.1 customers per second, which means like we're having basically in a minute, we're having 6 customers coming into the store. So high traffic. In this high traffic, high footfall situation, profitability is less. So the most interesting insight from this analysis is the following. Essentially, retailer, they swear by footfall. If you ask a retailer, what do you want to do? They say, I want to have more customers coming in. There's more customers coming in, they sell more. However, in an epidemic, you may want to not to discourage people from coming to you. And maybe then things like curbside buying and things can help. Because if you want to maintain high social distancing, what you will do is you'll position the products in a way that customers will not spend too much time in the store. So why this happens, why do we have this curve having low profitability? Because this would basically, you want people to spend a small time in the store, so and not to be too close to each other. So the model will position the products in a way that people come, they shop fast, and they leave. And this makes you lose profitability, no more impulse buying anymore. So, and this goes against the conventional wisdom of having a high footfall, but this is an epidemic. So in an epidemic, it might make sense not to encourage so many people to come to the store. And this is another graphic from the AI over here. Now, what happens to the allocation of products of categories to the shelves? They do change. So here we have 3 allocations. One that minimizes walking, one that maximizes impulse. Sorry, not walking. One that minimizes time in the store, one that maximizes impulse. And one of these Pareto optimal solution will maximize impulse subject to a value of the time in the store in the middle. So we see that the allocation of the shelves are changing. So if you want to follow our model recommendation, you expect that your store configuration will change significantly, basically. Okay. So the allocation of things would change significantly. Anyone knows why do we have that over here? This graphics on the right. Why does ChatGPT give me this?
And everyone bought a huge quantity of
Toilet paper. So supermarkets were known to have shortage of toilet papers in the epidemic. But anyways, so the shelves allocation changed a lot under different objectives, which is interesting. But what doesn't change very much is the traffic densities. So you move things around, but somehow, and we believe this is because our store is a little bit small, we could not really change traffic too much. So the traffics do not change very much except in a few shelves over here. So we believe maybe that we need a bigger store. So we'll have to again go now and hunt for a bigger store, more data. We're trying to do this right now, but it takes too much time and effort. Or we can try to synthesize some bigger data, but this is where we are at right now. We're not very happy with this finding. We believe that traffic should change more under different objectives. And finally, as final thoughts, so we have a promising area of research where we could come up with win-win solutions, I'm sorry, for both the retailer and the customer. So that's the major finding for today, is that using multi-objective programming, we can achieve win-win solutions with this Pareto optimal solutions. This is on the business insight. Technically, we have highlighted that there is serious need for more research into things like quadratic assignment, more work on spatial demand models, and so on. So people who likes to do computational work, this is a very fertile area for proposing algorithms that should reduce waiting time significantly, we believe. And that's the talk. Sorry, I took a bit more time.
Thank you.